So anyway, I'm so glad to be here to talk about my research. So today I'm going to share with you so some of the work from my group on river basin modeling. All right. So, oh, here we go. Yeah. So we can, for river basin, we can look at model river basin as a coupled nature and human systems. So with socio-economic development, so the coupling of human and nature components has been expanded from local to sub-watershed and to the entire watershed scale. So let's use ROC Basin. So this is probably some of you, maybe all of you have heard about this. So this is a very famous example about unsustainable river basin management in the world. So I just want to use this in the beginning of my talk. I use this basin as an example to show you the coupling of human and the natural component. Right? So in this figure, you can say, so this is the area of the lake. So this is the inflow to the inland lake. So ROC is an inland lake in Central Asia. And the two rivers, Amadaya and Serdaya, they flow to the lake. So this used to be the fourth largest inland lake in the world. But today it shrank to some small lakes. So in this figure, we can say some kind of companion relationship between irrigation development and the change of the inflow to the lake and the change of the area. And this figure here also show you the kind of relationship between the flow change, the area change, and the fish harvest change from the lake. Okay. So actually, I used this basin as a case study in my PhD thesis. So I did some work to combine economics with some hydrology together. We call that as hydroeconomic modeling. But the question which has been in my mind for over 20 years is the threshold here. So around the 1970s, right before 1970s, there is like a tipping point, like a threshold about the flow, the inflow to the lake and also the area. So why did the tipping point happen at this time? So if the irrigated land stopped increasing or had less increase around this point, what will happen? So this is actually it's an issue in complex systems about the tipping point and the threshold. And over years, I'm thinking about how could we model this? Is there any kind of systems model we can simulate the threshold and the tipping point? And then I really realized this is not just like a pure natural problem. We really have to combine the human component with natural component together to address this issue. Okay, so when we talk about models, river basin models or watershed models, so we always look at the history of hydrologic, watershed hydrological models. So this is a poster of Stanford model. Stanford model was developed, was released in early of 1970s, and it was called the first semi-distributed watershed model in the world. Okay, but if you look at this post, what do you find? So this doesn't look like, the post doesn't look like a natural watershed figure, right? It has some ecological components, it has a lot of human components. So that really means from the very beginning, at least among the mind of hydrologists at Stanford, they really mean if we want to have a reasonable river basin or watershed model, we have to some way combine both natural and human components. But unfortunately, on the models we have been using over years, no matter the old model like HSPF or HAC models or relatively new models. So all these models, to some degree, they consider human component like reservoir operation or land use change. But based on my knowledge, I may not be right, okay? I may not be right. Often they treat human impacts as a linear factor. So, but based on many research from recent years, the impact of human activity on hydrological processes is nonlinear. At some point, if you increase water use a little bit, you get a big change in the hydrologic processes. So you just saw that from the RC case, right? So now the issue is that how could we get a reasonable human dimension into watershed hydrological models? This is still an issue. This is still a big issue. And in recent years, we got a lot of interest on the human dimension of hydrology, right? I will mention a little more on that later on. Okay, so the question is, what is the next generation of models for river basin management? Okay, so I put this as actually this coupled nature human systems. This is a terminology used by U.S. National Science Foundation. They call proposals on this kind of studies almost every year. So in the very beginning, they said, if you want your proposal to be approved, you must split the money between social scientists and the physical scientists. Otherwise, you will not be able to even get, anyway, your review will not be good. They just try to enforce people from different areas to work together to really catch the dynamics of the interactions between H and M. But in the real world, this is what we do, right? So on the human side, we usually just assume water availability is known, all right? To some degree, we know water availability, either deterministic or stochastic. And on the hydrology side, physical side, we also assuming water demand is known. So this is what we did, right, in the history of water resources engineering. Assuming we know the water demand, then we design a reservoir, we design a water diversion project. But economists say, no, this is not right because water demand is not determined. Water demand changes with market, even at one time point. All right, so for coupled human nature, so CNHS, how can we discover processes that link human and environmental processes, environmental systems? Like in the RSA, how could we link the irrigation development with the change of the RSA? And then how could we include the interactions and feedbacks between human and their environment? And how could we understand the so-called emergence or the emergent properties at the systems level? Why does the threshold occur in 1970s for the RSA case? So I take that kind of threshold point as an emergence of the whole system. And this figure basically just shows some interactions and feedback. So we might just define 3 templates: human templates, abiotic, and biotic. Right? They're all driven by some external drivers: climate, globalization, etc. So as we can say, the human behavior, of course, also includes some policies. They might influence the frequency, magnitude, and form of human interference or the activities. And those activities were including both long-term and short-term activities. They will change the biotic and abiotic structure and functions. So we have so many examples on that, right? So with very extensive water use, then the ecosystems will be seriously affected. And then particularly in the biotic template, if we find if some changes are very intensive, and then that could cause the attention of the human side, human society. And then that will drive some policy or regulation changes, and that will, intent that will affect the human behaviors. So this figure just shows the kind of cycle of the the loop of the interactions of human and the nature components in a watershed. I like this figure. In this figure, we show the resilience, because the resilience of CNHS. So now in the resilience basically means the capability of a system to recover to a regular state or just shift to a new state under some new conditions, right? So here we use the concept of ecological resilience. So that basically means if the interruption is within a certain range, we call this as the range of the basin, then the state will, the current state will be maintained. If the interruption is over a threshold, then it will change to another state. Okay. All right. So given this conceptual introduction of coupled nature-human systems, so I just have this three statements some way have driven the work of my group. The first is how could we want to develop tools for scientific exploration towards the understanding of systems dynamics and towards sustainable solutions for river basin management. So usually, if we look at back the history of hydrology, and a lot of people say, oh, we are scientists. We just try to understand the insights. We try to make some predictions. And then there are another group where water systems engineers. So we try to develop solutions. But between these two groups, there is a gap. The reason I said that is they have different models. Right? They have their models may not necessarily interact to each other. So the other one is like, how could we develop physically and institutionally sound models? So we have spent a lot of time to develop distributed hydrological models. Right? So if you study hydrology, you should be familiar with that. But on the institutional side, we usually just assume some kind of lumped representation. I will show that. And the last point is that if we we just on hydrology side or water management side, some of those models are very difficult to solve. If we combine them together, then what the challenge on solution could be even worse. It could be even larger. So how could we develop a computationally tractable framework? That's also an issue, right? So now in the following, I'm going to discuss a little bit about the work in my group on how could we model the human dimension of a river basin using an agent-based model. Right? So in this figure, in this diagram, I want to talk a little bit about the comparison between centralized model and the distributed model. Okay? Use these two icons. And the figure here, so this picture here shows the people from different countries, representative from different countries in Danube River, right? So because they realize they have to manage the Danube River in a systems approach. They need to work together. But ironically, it's kind of interesting. Each one holds the picture of their own country. I assume if they put this picture together into the map of the watershed, this picture might be better, but they did not. so anyway, so that basically shows the management of the basin. We really have to consider the heterogeneity. We really have to consider the individuals with internal goals, right? That means representative from different countries, they are there to represent the benefits of their own country, although they intend to work together. Okay, how could we catch this situation in our modern work? All right, so then up to this point, I was just in my heart, I criticize my own work back to my PhD thesis. So in my PhD thesis, I use RSA Basin as a case study. I developed a huge model. I developed a huge one with 10,000 variables and a lot of nonlinear equations. And I worked with world-famous operation research professor, Professor Leon Nasden, and I eventually solved that model. So, and we published some papers on algorithms. I think that's my kind of contribution, kind of contribution to the literature. But when people ask, is your model really useful? I can say, all right, probably I provide the kind of ideal solution. An ideal solution. Assuming all sectors, all countries in this bed will follow a super hand, will follow an international authority. So that's like a centralized approach. But that's not possible. That's not possible. That was not possible even in the former Soviet Union period when all these republics belong to former Soviet Union. But today they are independent republics. It's not possible for all of them to follow a super hand. So institutionally, those models may not be realistic. Okay, and the other one, technology, from a technology perspective, or centralized model, assuming perfect information exchange. Perfect information exchange. That's not realistic in the real world either. Okay, so and also when we have this large optimization models, computation, algorithm is always a challenge over there. So since then, I have been thinking about how could we avoid those things and develop more realistic models. So I already mentioned agent-based models. So agents, we basically, so this kind of modern approach will recognize the role of individuals. And so we try to just combine individual behaviors and the systems structure and also the interaction between individuals and the environment. So in the literature for water resource management, we talk about bottom-up down or bottom-up or top-down management approaches. So to my understanding, I think this agent-based model, we try to first characterize, recognize the role of individuals. And then we simulate, we try to understand how individual behaviors, different behaviors, will form like a phenomenon at the system level. So basically, we would say this is a bottom-up approach. And also for agent-based model, we need to develop some roles for behaviors, and also sometimes we also need the roles to change those roles because those behaviors or institutions, they change over time. Okay? From a computer science perspective, we have another equivalent term which is called multi-agent systems. So the multi-agent systems, so this basically provides some technology for us to simulate agency intelligence over time. Okay. All right, so let me start with a little bit analytical work, and then I will show you some results with two actual river basins. So for a river basin, let's say we have a number of water users. And in this formulation, we just assume every water user is an optimizer. They try to optimize their profit or benefit. This benefit includes two parts. One part is that if there's no construction on them, they can use as much as they want. So that part is represented by Fi. And the other part, of course, in the real world, that's not realistic. They're always subject to some constraints, right? Or regulations. So this second part represents that the result of the environmental impact. And we can explain those terms for two systems. One is for the administered systems, and the other one is market system. So for administered system, we define Wi as water use permit of an agent. And then PL is the subsidy, PH is the penalty. So if you use more than the permit, then you get a penalty. If less, you get a subsidy. And for the market system, we define WI as water rights, and the PI defined as a selling price, and PK is pH is a binding price. Based on some assumptions, so here we have a set of equations with the same number of equations and variables. So we just proved if under a situation of water scarcity, okay, which is defined by the sum of the water right is less than the maximum water demand from the sum of the maximum water demand from all users. So in economics, this could be defined as water scarcity. So under water scarcity, we could find a solution. Okay, we could find a system solution, which is represented by the cap of these variables. So for here, we want to determine two things. One is the economic incentives, this high price or low price, and the other one is we want to define the water allocation. So another assumption is a market clearance. Okay, to define a deterministic analytical solution, we would assume the market clearance, and also the difference between the selling price, binding price, or penalty and subsidy. We define that as a transaction or administrative cost. So with these assumptions, we get an analytical solution for the system level benefits. Okay, so for the first item, this part is the sum of the benefit from individuals. And the second part is a combination of other factors, like the prices and also the difference between the actual water allocation and the water permit. So this equation actually shows three things. One is the agent autonomy. So that basically says if we improve individual utility, individual benefit, we could end with higher basin-wide benefit. And the second one is the interactions. So if we could somewhere reduce the transaction cost, and then we reduce this difference, right? Reduce this difference. And then that could end with a larger system level profit, benefit. The third thing is that if we have a perfect environment, if the water right, the initial entitlement, water right or water permit is perfect, is almost equal to the optimal system solution, then this part will be equal to 0. But this situation is not realistic in the world, right? So that's why we always try to encourage market solution or some kind of management solution to encourage people for water trade. Okay, so this analytical model just shows us, using an agent-based approach, which shows us some concepts on basin management. And then based on this analytical model, we designed an algorithm. So basically for this algorithm, we want to solve a basin-wide water allocation problem. We want to determine the economic incentive. So that's the pH and the PL. And we apply that to the Yellow River Basin. So this is a diagram of the systems network. It includes a large number of water use agents and also the reservoir agents. And especially we consider in the downstream of the Yellow River Basin, we consider the 3 ecosystems agents because this is a place we need some water, right, to maintain the ecosystem integrity. So we combine a hydrologic simulation model with this agent-based model. And through this loop, through this cycle between these two models, we determine the water prices at different places, at different months, and also the water use decisions. Right, so this figure just shows some results. So I don't have time to explain the details, but I just want to point out this water price is basically economic incentive. It shows in different months, in different places of a watershed, we should apply different economic incentives in order to, to catch the kind of maximum systems benefit. Okay. And also, so in this table, we just show in different months, what is the upstream water board or midstream and downstream water board. So you can say basically the downstream people, midstream and downstream groups, regions, they bought more water, right? They buy more water. And the upstream, they sell more water, right? And the difference between the water sold and the water bought is assumed to be used for the ecosystem's benefit, right? The ecosystem's use, for the downstream ecosystem use. And then we also, because we determined the price for each agent, and we could calculate what is the cost to maintain certain amount of water for the ecosystems in downstream. So the total number here is 2.95 million renminbi. This is 100 million renminbi. And this number is acceptable because this number, compared to what we're doing now, this number is much less than the increased GDP. Right? We account the GDP for the agriculture and industry water users, and we found with this price incentive, the GDP increase could be much higher than the water, than the cost for ecosystems. So that just provides some comments for the government to say, if we use this economic incentive, we might be able to get some money to pay the ecosystems. Right? So let me just move to another case. Another case study. This is a Republican River Basin in the U.S. Midwest. So this is one of the areas with most intensive irrigation in the United States. And the figure here shows the kind of coupling of the irrigated area. This is the irrigated area over different time periods. And this is the annual flow out of the basin. You can say anyway, they show some kind of coupling relationship between the two. And this figure shows the wells, the number of wells in Nebraska, Kansas, and also the upstream Colorado. So especially in Nebraska, there is a large number of wells developed over years. So this figure shows that in different periods, we compare the outflow at a particular location in the basin, in the downstream of the basin. So you can say over time, the average monthly flow has been reduced a lot over time. So this is a conceptual model for the agent-based model and the groundwater simulation model. So we have two different. We define farmers as agents. We also define natural resources districts, irrigation districts, power districts. Those agencies as some special agents, right? So. And so in this figure, basically shows we couple agent-based model with a groundwater simulation model, and there are some interactions between the two parts, and we try to simulate the co-evolution between the two parts. A little bit more details about the modeling. So here we have to consider the difference of the time scales of different models. We simulate the irrigation water demand, irrigation water use day by day in the irrigation period. And then we run the model flow to simulate water table month by month. And annually, we would update irrigated area and also the regulations change. So on the behavior side, so here there are several equations here. Let me just try to explain that. So basically in agronomy, we have the so-called managed allowed deficit. So that basically means for if you want your crop to maintain at a reasonable yield level, so the soil water deficit should be maintained at a certain level. But this level, we call this as MAD. All right? This MAD level, it varies by farmers. Some farmers, they are more sensitive to the drought, to the deficit, or they care their crops more. Some farmers, they are less sensitive. Right? So that means their behavior affects the actual value of MAD. So we just add that value as, so here we treat that as beta. So then you might ask, then how do you determine the behavior factor? So when we did this project, we used a statistical model. So based on a limited survey, and we just assume, we fit some probability distribution about the behavior parameter. So actually this parameter also is affected by the human behaviors, also affected by the physical situations, such as the soil type, right? The soil type and the slope. So you can say over years, farmers could develop some reasonable empirical knowledge based on the physical conditions. So in this one, I just want to show you a demo, which was developed many years ago. The demo is nice. Let me just do that again, sorry. To restart that, because it really shows the coupling of different components. So before I run it, let me show. So here we try to put. So this is a river. This is a river, and then we use this little man to represent the irrigation development, right? And this triangle means there is some violation of the water permit at different locations. And then we also show so here we show some parameters like the average water use, the crop yield, and the land value, the profit, and the regulation change, right? So now let me just start this, and so that's over time, the irrigation developed from the, irrigation, sorry, I have to, I cannot use this. Irrigation develops along the river because it's it's relatively cheaper to pump groundwater along the river. And then over time, we can say irrigation has been expanded to the areas further away from the river, right? So, and over these figures, we just say this is a regulation. So back to some years ago, the maximum permit is about 25 inches per acre per year. And then we also show the number of wells, increase of number of wells. So this is the cone group. And the mean, the average yield. This is the average yield, and this number shows the behavior, the beta, how behavior parameter increases over time. Okay, and below here, this shows the change of the river flow. You can say that basically the river flow is declining. All right. So eventually we say there is a decline of the permit. So that means because of the depletion of the river, the government decides to reduce the maximum pumping permit from 25 to about 13. So this is a demo. This is not an actual model, but it really we just want to use this to show the coupling of the human change, such as the regulations and also the water use and the natural, like a water table and the average stream flow. Okay. And it's also interesting to find out the behavior. So that's basically at some point the behavior parameter increases. So that means the farmers tend to pay more attention. They become a little more sensitive to soil deficit. So that is probably because of water is becoming more expensive, or water availability is more limited. All right, so let me look at the time. So we also did some scenarios. We just say if farmers are more sensitive or less sensitive to soil water deficit, what might happen to the groundwater depletion or the regulation change? And the results are kind of expected, because if we assume farmers are more sensitive, then the regulation might come a little later. Okay, might come a little later, because farmers, they're always doing something right. The government does not need to put constraint ahead of the time. Okay. And here we also simulate how if if farmers change their behavior, if farmers adopt some changes over time, how would that affect the crop yield and also the environment, especially in particularly groundwater depletion? So there were two assumptions here. First of all, we just sort of say farmers are kind of informed about their crop yield and the comparison of the crop yield to what they got in the past years, and they also notice the pumping cost. Right. And the other thing is that when farmer in a particular year, when yield is particularly low, and then farmers were considered to change their behavior next years. And those assumptions are kind of reasonable, but they may not be rare in the world, right? Because we always have some kind of bounded rationality in the real world. But here we just assuming, we make these reasonable assumptions and look at the results. So basically we say because of they also account the pumping cost. So that means even they become more sensitive, it doesn't mean they will get more profit, okay, more irrigated yield. But I mean, larger percentage of farmers will get basically increase of the crop yield. So the other one is that with the assumption, with this adaptation, with the changed behavior, we also found the farmers, they were, so that could end with some patterns of the groundwater depletion reduction. So in other words, this red arrows shows if farmers really follow those assumptions, and then the reduction in these 4 particular areas could be reduced. In other words, the groundwater situation could be better. Right? So in this figure, we want to show how human behavior change affects the spatial pattern of groundwater, of water table change, and also the crop yield. Okay, so as I just mentioned, to develop agent-based model, we have to figure out the behavior rules. Particularly, we have to figure out the change of the behavior rules. Those are not easy. So actually, there used to be a very big debate in some conferences. Some people say we just stay with optimization, classical optimization. We should not do this so-called agent-based model because we don't have data. We don't have enough data to figure out the rules, the behavior rules, right? But today, I mean, with social media, with the so-called big data, now we start to rethink about this technology, agent-based model, because we might be able to find a reasonable amount of data plus some technology, information technology. We might be able to find out some reasonable behavior rules. So here I just want to, so first of all, my group so in one of the projects, we simulate the farmers' response to biofuel development in central, in Middle West. And then in that frame, we just assuming the agents are smart, they could learn over time, and we implement a Basin learning framework and simulate. Basically, we just assume farmers' decision will be some way informed by observations, and then their perceptions about the uncertainties in market, uncertainty in climate will be improved over time. And we also, one of my recent PhD students, he developed some, so use this direct information graph to derive, to dig out the rows embedded or hidden in data, right? So basically we just got all kinds of factors on irrigation, pumping for irrigation. And then we use some advanced information technology like probability-based information graph to dig out what are the real rows over there. So here we based on his research, we found out in different places, we found different factors on irrigation. For example, in Colorado, we just found the change of the temperature is a major factor in Colorado. This is upstream Colorado. And then in some places, like pattern in number 2, pattern number 2 is that we found the change of the crop price, change of the temperature, and also the change of precipitation, right? So this change of precipitation change of the crop price. Those three factors jointly affect the groundwater pumping. And in some other places, we found out actually the crop price may not be a major factor, but the change of the water table in April 1st will affect the decisions. So briefly, in different places, we find out different roles. Right? Okay, and again, I like to go back to this figure. So what I want to summarize what I talked about. So what is the model for next generation? So we need scientifically sound. So that's like distributed hydrological modeling, which carries enough sufficient physical details. Right? So, and also we need institutionally realistic. So in my talk about I use agent-based model as an example. Right? So this may not be the only model you can use to simulate the human dimension, but that agent-based model could be an example to show like a more realistic institution. Plus computationally, some computational algorithms, we might be able to develop a model which could be used for both scientific understanding and management. And recently on the science side, there are many efforts. They actually they provide some support for this kind of modeling, like hydrology as an interdisciplinary science. So this is a paper published by a paper led by Richard Vogel at Tufts University, published in WRR. And also hydroformology. This is also a term from Richard Vogel. So basically, we want to some way follow the footprint of human activities in hydrological processes, such as ET or flow, recession, and those things. And then, actually, during lunch, we have talked a lot about social hydrology. I know the Water Institute is trying to hire a faculty member on this relatively new research area. It's called social hydrology. And my colleague, Professor Silva Pala, is leading this effort. So no matter what we call, as hydroformology or social hydrology, it is really important to put a more realistic human dimension together with the physical dimension of hydrology, and in the context of coupled human nature systems. And why could we do better? There are many, I would say there are many reasons, right? From the data side, we are talking about big data, social media with cyber infrastructures, models. We just talk about more on different social science models or physical science models. We have more better models than before, and also the forecast. The climate scientists provide us better forecast. All right, that's more like kind of assumption, okay? And the practices. So sometimes we will talk to practitioners, and their ideas are even more advanced than people from academic area. And then in many countries around the world, institutional change are moving toward to support more comprehensive modeling of river-based modeling. And then I just talked about the science, and then finally the information technology that provides a strong support. All right, so this is my last slide. So basically, I just want to say coupled nature human systems is a new systems concept based on physical and social sciences, and it facilitates new model formulation and solution algorithm for river-based modeling. And I try to show ABMs with some potentials in building scientifically sound, institutionally realistic, and computationally tractable models. And also, finally, I want to emphasize, so hydrologists or water resources engineers or water resource systems people, so we really should work together. It's really interesting to say some hydrologists, they focus on fundamental processes, and today they switch to systems problem. They switch to water management problems. And some professors, like I can mention one name, like Professor George Homburger. He was very famous for soil kind of soil study, right? Very, very fundamental process-based research. But in recent years, he moved to agent-based modeling of human behaviors. And actually, he has given a lot of talks about his agent-based model developed in Sri Lanka. And the other case is a lot of the water systems engineers, they are moving to hydrology. So like my professor, Danny McKinney. So I worked with him on River Basin modeling, but now today he moved to glacial hydrology. Because he thinks if we want to solve the problem in RSA or in Himalaya area, we really have to understand the glacial hydrology. So it's so interesting to say the people in different disciplines, different areas, they're coming together. So in 2015, Water Resource Research published a special issue on, for the fifth year's anniversary. So I'm the area editor for the systems and the policy area. I only invited 5 people to contribute. And because this system and the policy is relatively small area in WRR, in water resource research. But eventually, we publish about 60 papers. So it's very interesting. We publish over 20 papers on water resources management issues in general. So we have George Homburger, we have ours, George Kakos, we have Dennis Natmiles. Those people, they are invited to write something on fundamental hydrological processes, on legacy on processes-based research, but they wrote papers on how could we combine, how could we integrate different science, especially hydrology for water resource systems analysis. All right, thank you very much. I probably went over time a little bit.
Thanks. If I may, I have 2 questions. First one is, how did you consider the regional water management in terms of the spatial and temporal scales in your coupled model? And the second question is, how did you consider human policies feedbacks in the coupled model? Because let's say if today there is a flood and it will affect the social module, like the ABM in your model. And the humans will make policies to cope with it. And then how did you consider these feedbacks in your coupled model? Thanks.
Yeah, well, very good questions, very typical questions. Let me answer your second question. So simply speaking, right, to incorporate the policy change into models, right? So that part, I don't think hydrologists or water resource engineers could do a reasonable job. We need to work with economics, like Professor Brewer or some other social scientists, to incorporate their component, so coupling their component with our models. So basically, like we could work with them together to develop more reasonable agent-based model and couple that with our physical model to simulate, because their models, like agent-based models, they also simulate the policy changes, the policy responses to some like altered ecosystems or some other changing environment. Right? So for your first question, sorry, can you say that again? I'm not
sure. First question is, how did you consider the regional water management in terms of the spatial and the temporal scales in the coupled models?
Okay, so we have, good question, but I think it's very big. So we already have, over time, we have developed a lot of models, especially for regional or basin-wide water resource management, like the Yellow River Basin, right? If you go to China, you could have easily find like 20 models, right? So you either find they all say we provide solutions, or we analyze the issues of river basin, Yellow River Basin management. But now for scientists, for researchers, The question is like, how could we build our model based on science, and how could we make our model really used, not only useful? That's a challenge, to my understanding. So.
More questions?
Okay.
Thank you. Thanks for excellent talk.
Thanks.
I mean, I've been working this for a long time, so sometimes I see some of these being tackled in the past, but differently done now. So one thing I just wanted to clarification is your agent both at the farmer level and then also at the big farms level? You had something like 52 or something, but that seems like too few a farmer.
Yeah.
So
Yeah, sorry, that figure just is a conceptual model. So we did both. So in one of the project, in the demo, the demo I showed to you, that's like we have about 30 farms. But in another one, in the one later on, I showed some results. Yeah, that's basically, that has like thousands of farmers. So that's also kind of advantage of agent-based model. I mean, the size of the agents does not affect the computation too much.
Okay.
Yeah.
Just one other. So I'm wondering if you were able to include uncertainty information, uncertainty analysis or uncertainty information in the model easily? Is it different from conventional models? As well as, I'm wondering if you talked about even climate change and so on. For example, you have irrigation acreage going up, but levels going down. But so most of the loss is coming from evapotranspiration.
Yeah, sure, certainly, yeah. That's in one for, I only had one slide to show that. We published a paper in WRR about maybe 7 years ago to look like how farmers respond to biofuel development, how farmers choose their land for the mandate of biofuel development in Middle West. So in that one, we assume farmers will consider the uncertainty in the market, in the energy market, and the crop price and the crop market, and also the uncertainty of climate or weather. So we would assume so that's why we set up that Basin learning framework to simulate how farmers change their behavior. In Basin framework, we could identify a few parameters which could represent the farmer's behavior change over time. So that's a study we have done. Right. Yeah.
Can I ask one more question? So it is more on the computational issues. Are they more efficient or less efficient to do two things? One is make it much more parallel and distributed computing. The other one is, which means you can also hopefully reduce total CPU time for solving from old centralized model.
Yeah, that's very, very timely, important questions on the computational side. So for agent-based model, obviously the parallel computing could play a role. So actually, one of my PhD students, he published a paper in environmental modeling and software. So in that paper, he coupled model flow. Model flow is quite complex groundwater simulation model with an agent-based model. And he assumed agents are optimizer. That means he has to use nonlinear optimization algorithm to solve the model for each agent. So that's like hundreds of agents. So, and he put that online. I'm not sure if the website is still available anyway. So, but in that, the good thing is that he could use some cloud, based on some cloud computing, parallel computing, he made it work. And so we can say like the coupling of model flow with the agent-based model, we can run that over 20 or 30 years in a reasonable time. So, yeah.
More questions?
Thanks, Ximing, for a great talk.
Thanks.
My question was kind of broader. So in the last decade or so, we have seen, or even 5 years, we have seen a tremendous interest in the socio-hydrology or coupled natural and human systems.
Yeah.
But you're one of the, I would say, people who had worked on it for a much longer period of time from the start of your PhD, like you were saying.
Yeah.
So in your mind, for students who are working on this or interested in this, where is the field going? What do you think are kind of the frontiers of the field? And
Yeah. Well, thank you very much. This is a tough question for me. So, I mean, we should probably ask Siva to address that. So, but I sit in a systems committee with EWRI, and most of the people in that committee, they got very angry about the social hydrologists because they said, we have been doing this over years, right? We have been trying to, understand, similar policies or solutions. We already put human, because this is decision making, right? For decision making, we have to consider human side anyway. But Siva said, no, I mean, we are scientists, so we want to understand some insights. So basically, it's maybe I can put it in this way. So it's like a dynamics, right? So we simulate a system as a dynamic system, and in that dynamics, what is the dominant driving force for hydrologic alteration, and what is the feedback of that on the human side? So he said nobody has done that before in the systems area. So the systems area is you guys put optimization models or simulation models. You have some scenarios or you have some objectives, and then you run your model. You say this is the solution. So I think both are kind of reasonable. But my own understanding, my own observation is that. In order to advance social hydrology, we really need social scientists and hydrologists to work together. So for a workshop, this is social hydrology workshop, but we don't have social scientists in the workshop. I think that's kind of difficult. That's really kind of difficult for hydrologists to figure out this by ourselves. Sorry. Yeah. So that's one thing. And the other thing is I really think our systems people, so that's like the people who try to complain about the social hydrology, we really need to work with scientists. So for example, we develop a solution. So we should be able to explain from a scientific perspective why the solution is better, why the actual occurrence, the actual world does not look like this. We have never, as engineers, we have never thought about that deeply. Or from a modern perspective, we should be able to simulate what happened before we make a better solution. And water systems people, we don't think that is necessary. We just do optimization. This is a better solution. Use that. And then eventually nobody used that. So very briefly speaking, as I commented at the end of my talk, I just think these people, I would say basically we are the same people. We are both water resources researchers, right? So we should not some way just put some boundaries between different groups. We really should work together to develop more useful tools to support the community. So that's also, this kind of change has been reflected by NSF calls for proposals. So recently I was at NSF, I heard a presentation given by the deputy director of NSF. He said NSF now, we want to, traditionally we consider about the curiosity or processes-based science, but now we need to think a little more about users-inspired science. So in this way, in order to do that, we really have to our scientists should be noticed that the community engagement is so important. So that's what they said in the feature, like NSF research centers will be some way based on these principles. So I see some change, really. It doesn't mean I don't like social hydrology. Anyway, I think this is a nice word. Anyway, so.
Thank you very much.
Yeah.
I think we should give him another round of applause and then stop because this taxi will be leaving soon. Thank you so much.
Okay, great. Yeah, thank you very much.